Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with the second part of AC voltage controllers, whereby we have this at the beginning of the AC voltage controller video. I did share with you that we have two control techniques, which is the first one will be the phase control. We have covered that in the previous video on the phase control, and the final one, the second one will be the integral cycle control. Okay, so it's just a technique how to control the thyristors, the two thyristors. We're still on the same inverse parallel connection circuit, but now we're going to have a different control technique for thyristor 1 and thyristor 2, right? And therefore you're going to have a different output voltage waveform, but it is still periodical, and therefore we can have a level of a different level of RMS voltage and also the fundamental of the output voltage, right? Okay, so I've already, before that, I'm going to share with you that I've already uploaded the notes to the Padlet. The first one will be the lecture note, and then I'll also put in the PSIM simulation, right? Circuit you can download from that link to get the PSIM circuit, and then you can study how the control is done. And finally, I also have this MathCAD. So I hope by now you have already installed the MathCAD, and then try to use them to calculate to whatever equation that you have in your notes, right? So I've already put that, so make full use of all these documents put in the Padlet. All right, so now let's have a look at what is the AC voltage controller with an integral cycle control technique. Okay, so in this integral cycle control, you're going to have the key point here is that this is your supply, which is a normal supply, 240 volt, 50 hertz, right? So this is a frequency of the input. However, you're going to see that the output, right, the output across this load, the frequency of the output will be much less than the frequency of the input, right? That's the main observation, and therefore there are 2 points here whereby the output will be a different level of voltage as well as the frequency, right? The fundamental frequency. Okay, again we have an input of 50 hertz, but the output in this example, going to have 5 hertz only. Okay, the output only consists of 5 hertz compared to the input of 50 hertz, right? Okay, so now let's have a look how it's been done. Okay, so to be able to get that, we know that the input is 10 times faster than the output frequency, isn't it? 50, and this is 5, so therefore the input is 50 hertz higher frequency compared to the output. So therefore here you're going to see that there are 10 cycles of the input voltage. Okay, there are 10 cycles of the input voltage. 1, then we have 2. Okay, so you have 1 here. Sorry, I think it's better for me to 1, and then you have 2, 3 cycles, 4 cycles, 5 cycles, 6 cycles, and 7, 8, 9, and 10. Okay, so we have 10 cycles, faster than the output frequency. Okay, the input is 10 times faster. So if I can show you the waveform, there you are. Right, so this is supply voltage 50 Hertz. We have 10 cycles for the output. So now your output, look at this waveform. So you're going to let the input to be turned on, okay, for in this example you have 6 cycles. Okay, 1, 2, 3, 4, 5 and 6. So you can turn on the thyristor 1 and thyristor 2 such that the output will see 6 cycles of on voltage, right? And the other 4 cycles, so this is another 4 cycles here, 1, 2, 3, oh sorry for that. Okay, so these 4 cycles, the two thyristors will be off, and therefore the output sees only 0 level. Okay, so therefore this output waveform is slower than the input voltage, is that it? Because now your output will see this as your fundamental frequency, and then it repeat again for the next cycle from there to there. Okay, so this is the first cycle and this is a second cycle with respect to the output voltage. Okay, so now we're going to have another parameters here. To turn on the thyristor 1 and thyristor 2, we're going to have a different pulse signals to your thyristor 1 and thyristor 2. So V3 actually the pulse to your thyristor 1, and V4 is the pulse to thyristor 2. Okay, so since the now your output frequency is 5 Hz, therefore the thyristors also consist of 5 Hz frequency. Okay, normally in the AC voltage controller we have the same frequency, isn't it? But for the integral cycle control, the frequency of the thyristors is depends on the output frequency. So in this case, it is a 10 times slower. The output is 10 times slower than the input frequency. Therefore, you divide by 10, then you get 5 Hz. Okay, all right. So now we have this definition whereby n is actually number of cycles. Okay, so how to determine number of cycles? This is T supply, the period for your supply frequency, and then T load is the supply frequency, the period for your output voltage. Okay, so they have a different frequency now. So supply is the frequency of the supply is higher than the output frequency. Okay, so n, how to determine n? You have T on divided by T supply. Okay, T on divided by T supply for that cycle. Then you get number of cycles. Okay, for example, in this case, you can divide it. The supply is 0.02 second. Okay, then you get number of cycles there. Okay, and for m is how long, how many cycles the thyristors are off. Okay, and that will be defined by this equation. T on, should be T off. Sorry for that. Can you? Okay, this should be T off, not T on. I made a mistake there, sir. Okay, so it's T off over T supply. Okay, how many cycles off, and then you divide by T supply. And the total number of cycles for the output, this is actually for the output. Okay, this is the output number of cycles. So you just simply add number of cycles for turn on, number of cycles for turn off. So study the PSIM circuit that I gave it to you, how to provide this pulse. Okay, so now you have to think of that we're going to have this as 360 degree. Okay, so you're going to have here the 360 degree will be from there to there, the output, which is also equals to 5 hertz, isn't it? And you have the input supply as a 50 hertz frequency. Okay? So now when you want to trigger thyristor 1 and thyristor 2, we need to follow this 5 hertz. Okay? The 5 hertz. So if you look at the circuit again, okay, your output frequencies now is 5 hertz. Okay? And the input is 50 hertz. Okay? They have a different this one as well, 5 hertz. Okay, different frequency. So when you want to trigger the thyristor, you must be based on 5 hertz frequency. Okay, so we come back to the waveform again. Okay, so to get this 6 cycles, now you have n equals to 6 cycles, 1 2 3 4 5 6. And again, n is defined by T on over T supply, and then you have T off m, the number of off cycles, equals to 0 to, this is off, isn't it? Off over T supply, and then the number of cycles for the whole, for the output will be n plus m. All right, so therefore again, so this is 360 degree, right? So if you want to trigger thyristor 1 thyristor 2, you have to properly consider the cycles and also the degrees to trigger the thyristor 1, the angle to trigger the thyristor 1 and thyristor 2. Okay, so therefore if that is 0, this will be 180 degree, and that will be 360 degree. And for the 180 degrees, so if you divide by 5, and because you know that for 180 degree you're going to have 5 cycle, 1 2 3 4 5, isn't it? So if you divide 180 degree by 5, you will get one cycle will consist of 36 degree. Okay, one cycle will be equals to 36 degrees, and therefore if you want to trigger thyristor 1, you're going to trigger thyristor 1 to be turned on at this particular point, and then you trigger thyristor 2 and you turn on this, and then you continue with triggering thyristor 1. Okay, and then you alternately trigger thyristor 2 until at the end of the n cycles. Okay, so you alternately turn on thyristor 1 and thyristor 2. So I'm going to mark all this is thyristor 1 on. Okay, and this is where thyristor 2 is on. Sorry for that. Okay, there you are. So this is where thyristor is on. I'm going to mark as a thyristor 2, and this is where thyristor 1 is on. All of this. So you turn on alternately thyristor 1, thyristor 2, thyristor 1, thyristor 2. So look at this pulse. This is thyristor 1 on, thyristor 1 on, thyristor 1 on, on. And then you're going to trigger thyristor 2 here, 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 there. Is that it? So if you want to look at the PSIM circuit, then you get a clear value. Therefore you have 0, then you have 36 degree there, and then plus 36 you have 72, there, 108 here, 144 here, and finally you have 180 degree. You trigger thyristor 1, and for thyristor 2 you will be triggering at 18 degree, and then plus 36, 44. Sorry, what else? You have 36, 7, 80 degree, plus 36, so you have 1, 1, 6, isn't it? And then 36, 34, 1, 5, 2. And then again, last one will be the 1, 36, 1, 8, 8, isn't it? Can't remember. Okay, so you just simply 36 apart from each other. Okay, 36 apart from. So when you do that, then the output will consist of these 6 cycles, and it will be turned off for 4 cycles. Right? So this is how you're going to do that. Therefore, if you focus and look at the output, it is continuous, it is repeating, okay, but the frequency is slower than the input frequency. Right? So let's look at the next slide. Next page. And then this is the harmonic spectrum of the output voltage. So if you take the harmonic spectrum, look at doing the Fourier analysis, then you can see that yes, we have a supply frequency of 50 Hz, but now the load consists of, this will be the fundamental frequency of the output, which is 5 Hz. The input, the fundamental output input is 50 Hz. The fundamental for the output will be at 5 Hz. Okay, and just please ignore this, and you can actually put a filter to remove all this frequency, right? Okay, so now next, and for the harmonics, of course you want to look at the harmonics. So if you want to find what is the C1 for the output, if you want to get the C1, isn't it? C1, which is at 5 Hz of the output, then you can look for this equation, derivation for the fast Fourier analysis, A1, AN, and then you perform the BN. Okay, so it's already there for you, so you can prove it if you like. And then finally you can see that the output, the C1 or Cn, the component, equals to 2V peak multiplied by T divided by pi T squared minus N squared sine N pi N over T. Okay, sine N pi N over T. Okay, so therefore T, again, all this T and N is in cycles. N is number of harmonics. This capital T and N is number of cycles. So T is the number of cycles for the output again, and N is the number of cycles turned on for output again. Right? You can find this. So in this example, I show you that we have 5 Hz. Sorry, the fundamental, the second harmonics, third harmonics, and fourth harmonics. This is when I zoom. We zoom the waveform here. I'm just simply zoom this waveform, okay, and magnify that waveforms, and you begin seeing this first component. So this become fundamental, second harmonics, third harmonics, and fourth harmonics. And look at the frequency of each harmonics. This is fundamental, 5 Hz, second, third, fourth. Okay, so just to show you the example of how to calculate that, I use the MathCAD again. You can look at the original, examples that I give it to you, share with you from the Padlet. Try to run it, and then you're going to see that this VRMS input, Okay, the supply, F supply is 50 Hz, F load equals to 5 Hz, and this is number of cycles, and therefore you can find C1, right? C1 equals to 20.758. So if you refer to this waveform again, then you will see that there is around 20 something, isn't it? Yeah. And for C2, 13 point, okay, 13.23. So therefore, if you trace for this, you will get about 13 volt at the output. This is slightly higher. Okay, it is for third harmonics is about 13.957, and finally for C4 is 24.64 volt. Okay, so this is 34. Right, so you can use this equation to get the harmonics. And finally, for the RMS load voltage, you can use this. Okay, to get the load RMS is a square root the mean. Yeah, this is mean, and then you square, isn't it? So it is again V peak sine omega t to omega t. Solve for this, and finally you find out that the load RMS equals to V peak over square root 2, or this is also the RMS, isn't it? This is also the RMS, V as RMS. So in this case, if you put it 240 volt, and that is 240 volt. Okay, and again multiply by square root n over t. So again, both are not in second, but number of cycles. Okay, n number of cycles, t number of cycles, and then you can find the average power is given by this equation. Okay, and finally your the power factor. Yeah, you just simply output divided by input here, V load RMS, V peak square root 2, and you can find out that this power factor can be determined by just simply square root n over t. Okay, and there is a comparison between integral cycle and phase angle control. For phase angle could be used to control light, but integral cycle unsuitable for light control because you have a light dimmer due to presence of subharmonics components, because it's the different level of harmonic, isn't it? Different level of fundamental at the output, and also the subharmonics. This is known as subharmonics. Okay, all this is subharmonics here. Okay, second, fourth, this is known as this subharmonics. Could be used for motor, unsuitable for motor control, motor wheel cogging. Again, because of this, we can see that there is a different frequency as well as the lot of harmonics, isn't it, for the output. And then could be used to control heaters, suitable for loads with large thermal time period, such as electric furnace, isn't it? This is reflect to the slow frequency of the output. When we have a slow frequency of output, the time period will be large. Okay? Time period will be large. Generate radio frequency interference, no radio frequency interference. Effect of voltage drip, ripple voltage is less. Voltage dip is due to initial large starting current. Significant effect due to the harmonic dips because of subharmonic components. Okay, and I give you the example as well. In this example, an integral control technique is applied on operation of 50 Hz single phase AC voltage. Therefore, this will be your VF supply. Okay, this is F supply. To maintain the temperature, the heating system must be connected to the regulator for a few milliseconds. Look at that. And disconnected. This is on. It must be connected, which means on time. And it is disconnected for 40 milliseconds. So this is when it is disconnected, T off. Okay? So therefore, this 40 milliseconds is actually T off. It's already mentioned here. If the RMS input voltage Vs and the RMS output voltage of the regulator are 230 volt and 194.39 respectively, answer this following question. Calculate the number of T cycles during turn off. So you are already given 40 milliseconds, and we know the F supplies, then you can find the number of cycles for turn off. Calculate the number of cycles N during turn on time. So we know this equation, the load RMS, okay, V out equals to V RMS, Vs supply RMS multiplied by if you refer to the notes before, you have V peak, isn't it, over square root 2 multiplied by N divided by T. Yeah? So we also know that T equals to N plus M. Alright, so you can calculate and solve for N. So N equals to 5. The number of N is 5 cycles. And finally, the T on value is 100 milliseconds. So you can calculate from this, you can get 100 milliseconds turn on, and sketch the instantaneous voltage. So this will be the output voltage waveform. So whereby this, again, I'm going to stress that this is 50 Hertz from there to there, and this is, you have to actually F load equals to 1 over, so T load will be equals to 140 milliseconds, isn't it? So just divide by 140 milliseconds. So that will give you the output frequency. Okay, so that is very much what is integral cycle control. Again, I'm going to show you quickly show you the example PC. Right, again, this is 240 volt multiplied by square root 2 to give you the peak value and 50 Hertz. And for the thyristor 1, thyristor 2, here, look at thyristor 1. We can see again 0, 36, 72, 108, then 144, 180, and that's it. Okay, so that is for thyristor 1. And for thyristor 2, you'll be triggering at 18, 54. Just focus on the front numbers. 18, 54, 90, 126, the rest. I think I've made mistake in the explanation. So it's 18, 54, 90, 126, and then what else? 162, and finally 198. 198. So this is the pulse to your thyristor 2. Just now I did mention to you. So you have 0. You have 18. Then you have at 54. Then you have another 90 degree. Great. And then you have 126. And then 126 plus 36, 5, 162, and finally 36, 198. Right? So this is part for thyristor 2. Okay. The output, then if you run it, supply first, then we're going to add another screen, which will be the load. Okay, so supply voltage, load voltage, and then you just hit this FFT, and there you are. You can see the harmonic spectrum now. Adjust the frequency. I'm just going to see a few. So just try 500. Do you get? Okay. and I can adjust more to 200 hertz. This is what I'm going to get. Okay, so we have, this is fundamental 5 hertz, and then this is second about 10 hertz, then 15 hertz, then the one is 20 hertz here, and this is the frequency for 50 hertz. Okay, so we can simply, actually, if you use a filter, you can filter this out, a large filter, move that, and then you get the nice 5 hertz output. Okay, so give a go, give a try, and then look at the simulation simulation parameters, try to understand what is this example. Okay, all right, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.